Andrew, very good morning at Canada. You are muted, I think. कशात आहे रे? Yeah, I did it.
Okay, good. All right. You can hear me now.
Very good morning at Canada, I think.
Good morning to you. Thank you very much.
So actually, our scheduled time is 7:30. So most of the participants are still joining. So we'll start after 10 minutes.
That's fine. Yes, that's good.
Yeah.
So, thank you very much for all of your work in organizing this event. It's been.
Thank you. You are sparing your valuable time and you have given consent. Thanks a lot for the same.
Oh, it's my pleasure. I wish I could attend more of the sessions because the time difference is very difficult.
Yeah, exactly. Actually, we tried our best to match with the participants' time, so that's why it was very difficult to match the time with USA and Canada itself.
Yes, especially Canada and the US. Yes. So I did join the session this morning.
Yeah.
I enjoyed that very much.
Most of the participants from Nigeria, Israel, Iraq, Nepal, Bhutan, Afghanistan, Pakistan, Bangladesh.
Wow.
So that's why it was necessary to match the time with these countries particularly.
Yeah. No, I think it's good. It's challenging to organize an international event, so you've done very well.
So we'll start in 10 minutes. Before I'll just give alarm that we are just starting the session.
Can I just test if I can share my screen?
Yeah, sure, please.
Okay.
Yeah, sure.
Okay. Good.
So meantime, actually, this is our organizing team, Dr. Paslawar. I think you are not getting his picture. Yeah, he's Dr. Paslawar.
Hi. Nice to see you.
He is the chief scientist at Center for Organic Agriculture and Research and Training that we have established during 2010 at Dr. PDK.
Yeah. So how many people are in your research institute, the Organic Training Center?
Multidisciplinary. Actually, it is multidisciplinary. It's a team of 10 people, which consists of agronomists, plant pathologists, entomologists, soil scientists, horticulturists, dairy scientists, and one breeder also.
Yeah, and all focusing on organic?
Yeah.
That's excellent. Yeah, that's very good.
We have devoted total. We have devoted around 5-hectare land totally for this organic trial since last 4 years, and we are just thinking to expand the same in next few years.
Okay. And do you teach courses at university level there as well?
Actually, we had started one certificate course on organic agriculture. So around 3 batches have already passed out, and most of them have started their own enterprises. Because they are in manufacturing of bioagents, bioinputs, and some of them accommodated in organic industries also.
One course on experiential learning module for BS agriculture at graduate level.
Graduate level, yeah.
MSc and PhD students, they are also working on this organic part.
Yeah. Sorry, I think our connection is a little bit poor. I'm getting not very good sound quality. But it could be my internet. I'm working from home as a result of COVID. But hopefully it will be okay for the presentation.
Yeah.
Okay. Excellent. Did you get my last copy of my presentation I sent yesterday?
Yeah. I have received it.
Okay, good.
Then second is Dr. S.D. Zadav. He is a soil scientist and looking after the long-term fertilizer experiment.
Ah, yes, good. Excellent. Yeah.
Left to me, Dr. Vikas Gaud. He is a weed scientist, particularly working on weed.
Weeds, okay, nice. Oh, that's excellent. Certainly weeds and soil fertility are two of the biggest challenges in organic agriculture. So very important, yeah.
Then one more, Dr. Yogesh Ingle. He is one of the plant pathologists at Organic Agriculture Research Center. And he is
Excellent, yeah.
working on trichoderma and all the whatever the disease management through organic inputs.
I very much enjoyed your presentation this morning, your video. It was very.
Thank you, sir. Dr. Hadore is looking after the micronutrient research work.
Micronutrients, nice. Yeah, very important as well. And your soils, our soils, we don't have as many issues in micronutrient deficiency here, just the nature of our soils. But I'm sure with your soils, more tropical soils especially, there would be much more concern. So, and a longer history of farming, and yeah, so very important, yeah. It sounds like a good team. You have a very nice team.
Mr. Parikshit. Yeah, he is the man behind the curtains.
Sorry? Say.
He is the man behind everything, whatever plan we have made here.
Oh, okay. So, yeah, good. Yes, we need those people very much too. Yeah. Very
He is a soil scientist at Organic Research Center.
Man, true to my heart, soil scientist. I first studied in soil science, so very nice. Yeah.
So, Dr. Prashant Joshi, he is horticulturist.
Hi, nice to meet you. Some of my last work I've been doing is a little bit in horticulture, which I never trained in, but it was some of the organic farmers wanted me to work in small fruits. Yeah, it's very interesting work. Excellent.
So this is our
Vegetables
team.
or fruits?
Sorry?
Was that vegetable horticulture or fruit horticulture?
Fruit and vegetables both.
Both, yes. Okay. Excellent. Okay.
Thank you. Thank you. Nice to see you.
Nice to meet you.
So shall we start, Andrew?
Yes, please.
Okay. So very good evening, friends, and good evening to good morning to Andrew itself, because it's morning in Canada. So friends, again we have a very eminent speaker from Dalhousie University, Canada, and I warmly welcome Dr. Andrew, and on behalf of Dr. Punjabrao Deshmukh Agriculture University, Dr. KDKV Akola. It's in Maharashtra province of India, and we are very much associated with education, research, and extension education. So, friends, really, actually, I appreciate the enthusiasm of all the participants that they have joined in the evening itself, because in most of the countries and India too, it is evening now. And in the morning session, they have just experienced the Dr. Paola from Italy and Dr. Yogesh Ingre from this university. So this is again an opportunity for we people just to listen Dr. Andrew, because whatever presentation Dr. Andrew will be giving, it is really a sort of food for knowledgeable food for all the participants. So at this juncture, I would like to request Dr. S.P. Zadav, who is a coordinator for this particular session, along with Dr. Vikas Gaud and Dr. Devi Mai and Dr. Bhagwan Sonone. So I request Dr. S.D. Zadav to proceed further with the introduction of university as well as introduction of Dr. Andrew, please.
Good evening, friends, and good morning, Dr. Andrew, and very warm welcome to all. I am Dr. S.D. Zadav, Associate Professor, Department of Soil Science and Agricultural Chemistry, Dr. Punjabrao Deshmukh Agricultural University, which is popularly known as Dr. PDKV Akola. The university was established on 20 October 1969 with its headquarters at Akola. This agricultural university was named after the illustrious son of Vidarbha, Dr. Punjabrao Deshmukh, who was the Minister of Agriculture, Government of India. The university is situated in the central part of the India, is an eminent agricultural university, mainly working in rainfed agriculture. The agriculture in the jurisdiction of the university is dominated by the small and marginal farmers, is facing various challenges as drought, climate change, globalization of trade and economy. Cotton, soybean, paddy, pigeon pea, black gram, green gram, and other oilseed crops are the dominant crops of this particular region. University has great network across 11 districts in the Vidarbha region and imparting education through various agricultural colleges and conducting site-specific research since 1969. Similarly, 13 KVKs are the major pillars for dissemination of technologies of this university. This is all about the Dr. PDKV Akola. Now I would like to narrate about brief introduction of Dr. Andrew of the today's distinguished speaker. So we are very fortunate that we have Dr. Andrews for today's online webinar for presentation. Dr. Andrews Hammermister is the Director of the Organic Agriculture Center of Canada, OAAC, and Associate Professor in the Faculty of Agriculture at DALHOUSIE University, Nova Scotia, Canada. He has a bachelor degree in agriculture with a specialization in soil science from the University of Saskatchewan. He completed his master's degree in land reclamation and PhD in applied ecology from the University of Alberta. Dr. Andrew has worked with the Organic Agriculture Center of Canada since 2002, collaborating in research on grain and vegetable and fruit cropping systems, exploring soil fertility and weed management. Most recently, he has been studying small bush fruit such as HASCAP, landscape biodiversity, and applications of smart technologies to organic agriculture. Dr. Andrew is the Science Director for the Organic Cluster, the Coordinator National Initiative for Organic Agriculture Research in Canada. He sides on the National Organic Standards Review Committee and several other organic sector committee nationally and internationally. Dr. Hammermister is currently working towards identifying and addressing organic research priorities across Canada, linking the needs of producers with researchers and funding agencies. So this is all about Dr. Andrews. So I request, with the permission of this organizing committee, to start this presentation. Dr. Andrew, please.
Thank you very much. I will share my screen. Okay, am I sharing the screen? Is that good?
Yeah, please carry on.
If my internet quality becomes poor, I might turn off my camera, but I will try and proceed. Okay, so thank you very much for this opportunity. It's a fantastic event, and I really appreciate the opportunity to speak. I've only had one chance to visit India, and that was for the Organic World Congress a couple of years ago in Delhi. And so I've had limited exposure to India, but our institution, our Faculty of Agriculture does have collaborations with institutions in India as well. And I'm very pleased to establish this connection between our organic centers. So it's very exciting for me to be here today. I very much enjoyed the presentations that I've attended so far. The time difference makes it difficult for me to attend all of them, but it definitely has been inspiring, and I attended the sessions this morning. A little bit about the Organic Agriculture Center of Canada. It was already introduced, but our center is located in Eastern Canada in the province of Nova Scotia, right on the Atlantic coast. And our center was established in 2001. And we do conduct research to some extent. Our role has evolved, however, and much of what we do is work as the national voice in Canada for organic science, which includes coordinating science programs, linking researchers together, promoting organic science to government and to industry, and also establishing research priorities. And we find that this is a very important role to have within a country, to have a voice that is speaking on behalf of science, that's a coordinated voice. We also do a lot of knowledge transfer in terms of making the science that's being produced accessible to stakeholders who can use it. Lastly, our center has also established a certificate of specialization in organic agriculture, and this consists of degree level courses that are all offered online on the internet. So if you chose to take these courses, you could actually enjoy them yourselves. So I'll move on to my next slide, which one of the major projects that our center helps to coordinate is the National Organic Science Cluster. If you're interested in learning more about organic agriculture or the science of organic agriculture in Canada, I encourage you to visit the website that's shown here for Organic Science Cluster 3. And within that page, you will find a list of all of the different universities and government institutions that are working on organic agriculture in Canada. Right now, we are administering a 5-year program that spans projects right across the country. And we are soon going to be starting to prioritize our research for the next Science Cluster program. So the title of my presentation today is organic the interface between smart agriculture and ecological intensification? And I liked the title that you have for your event, which is From Field to Fashion. And smart agriculture, one might describe as being maybe a fashion right now. Is it just a fashion, or is it our future, is a question that I'll be asking. So my presentation will introduce you briefly to ecological intensification, which Dr. Migliorini has spoken to very well this morning, and so in terms of agroecology. But I want to link that to smart agriculture. And most people that I speak with might have a general idea about what smart agriculture is, but not very many of them have a very clear understanding. I was one of those people, and I'm not an expert in smart agriculture, but rather I want to learn how we can adopt these latest technologies to help support organic production systems and our research in organic systems as well. So, so this has been part of my exploration, and that's what I am going to share with you today. So Dr. Migliorini had presented a very similar petal diagram this morning from another source, Reginald's source. This is an example from Sofert and Ramankutty. And essentially, it identifies the 4 main categories that we consider when we think about the impacts of agricultural systems. And often when I speak into conventional agriculture, they are very focused on yield and then profits. And organic agriculture is interesting to me because it covers many more issues, and it also considers environmental issues, producer issues, and consumer issues. So each one of these petals represents a different issue and how organic might affect it. The red circle represents the conventional norm, so that would be considered the standard. And if the petal exceeds the red circle or goes beyond it, that suggests that organic is performing better than conventional systems. And as the petals indicate, most of these services that organic agriculture provides are exceeding the performance of conventional agriculture. However, we also have a high level of uncertainty. Many of these variables have not been very carefully measured, and they can be quite variable across different production systems and among different parts of the world or even parts of the country. So there's still much more research and improvement that we could be making in terms of agriculture. Now, one of the key challenges that we have is yield and productivity. And certainly if we want to see organic agriculture expanding, it is always beneficial to have a yield increase. However, we also, I think, perhaps more importantly, want yield stability, especially in the time of climate change issues becoming much more prominent. I think that we're going to have many more extremes in climate issues and pest issues, and we need to have resilient farming systems that have stability in yield should be our first goal, and not necessarily super high yields. So I think that we do need to continue to research this and study it and better understand how we can achieve better and more consistent performance. So what are the production barriers that are facing farmers? And again, we want to have reliable crop performance. Many farmers are not moving to organic because they are not confident that they will have consistent yields and therefore consistent profitability. We do also see very commonly that soil fertility and soil health are sometimes limiting in organic systems, especially in terms of fertility, since we're not using nitrogen fertilizers. Weed management is another critical factor that is important in organic systems, as well as insect and disease management. I'm not a livestock expert. I will not speak too much about livestock production today. I will touch on it, but certainly if we want to have organically acceptable livestock production, we need to be further understanding animal welfare issues and the support systems that are needed in livestock production. So IFOAM Organics International, which was introduced very nicely by Dr. Migliorini this morning, identifies 4 principles that we need to follow. One of those principles is the principle of ecology, and that's the one that I will be focusing more on today. And Dr. Migliorini had also mentioned Organic 3.0, which is the next stage in the evolution of organic agriculture. Within that framework of what the future of organic agriculture looks like, there are 6 features. 3 of those features are listed on this slide. That we must adopt a culture of innovation, that we must adopt continuous improvement towards best practice, and we need to be inclusive of wider sustainability interests. So with these 3 features in mind, I'm giving this presentation. So let's talk about the concept of ecological intensification. And again, this builds very nicely on the presentation from Dr. Migliorini. ecological intensification is based on managing service providing organisms that make a quantifiable direct or indirect contribution to agricultural production. So they are supporting and regulating ecosystem services provided by these organisms can be incorporated into cropping systems such that production is maximized while environmental impacts are minimized. So essentially what we're doing is optimizing the agro-ecosystems so that we can have optimum productivity so that we are still working within the limits of the agro-ecosystem. When we look at what that means, ecological intensification is usually characterized by high internal regulation processes, moderate uses of resources, and low losses of nutrients. And all those would also result in higher productivity, hopefully. So in other words, we're not purchasing and applying a lot of inputs. We are instead trying to optimize the cycling, understand the ecosystem that we're working within and optimizing it. So let's take a look at some examples of this. And as was pointed out this morning by Dr. Miglerini, the soil is the foundation of organic agriculture, and it should be considered the foundation of all field-based agricultural systems. And one of the key aspects of organic agriculture is that we appreciate and I guess mostly appreciate that there is a very strong interaction between the plants and the soil biological, chemical, and physical properties, but especially the biological properties of the soil. There are so many organisms in the soil that can influence plant growth, either by protecting the plant or by supplying nutrients or stimulating the plants or providing growth hormones or so on. So this is a key aspect of organic agriculture, and I think this is one of our greatest unknowns in terms of how we might be optimizing our production. If we're thinking about ecological intensification, we need to be thinking about how we might transfer or optimize the use of soil biology and optimize the biology in the soil to ensure that we have good, resilient, productive plants. So a common one that we talk about is our mycorrhizal fungi. And we have definitely seen research that has demonstrated that organic agricultural systems tend to have higher mycorrhizal fungi. And these fungi, for example, are very important because they develop relationships with the plants and they allow the plant roots to essentially explore more of the soil and capture more water and access nutrient resources that the plant may not otherwise be able to access. So the organic production system tends to support mycorrhizal fungi. We do know that excessive tillage can be detrimental to mycorrhizal fungi. And we also know that high phosphorus applications through fertilizers can also inhibit this relationship from forming. However, if we are wanting to manage our fields in a lower input environment, then we need to be promoting these kinds of relationships. This morning, Dr. Jogesh had given a very nice presentation about trichoderma, so I do not need to go into detail here. But this is another example of how understanding the mechanisms, the organisms that live in the soil, how we can extract those organisms and make good use of them to either promote plant growth or at least inhibit other organisms from being problematic. We're seeing more and more preparations, biopreparations and biostimulants and microbial inoculants becoming available in organic agriculture. And these are interesting to work with and sometimes challenging because we do not always see a consistent response in our crops to these treatments. And this could be because there's other factors that are limiting the plant growth, and so the plant can't respond to these treatments, or the soil is already quite healthy and the supplementation with these treatments is not providing an added benefit. But nevertheless, I think that we are still learning how many of these biological preparations can stimulate and support plant growth and help the plants become much more efficient. In terms of ecological intensification, we've also talked about pest management and trying to understand pest and disease cycles, and which is really important to understand where these pests come from, what conditions they are living in, and also what biological controls exist in our natural environment that we can help to enhance. And so here in Canada, we do have research that's going on relating to trying to enhance habitat for predatory insects of insect pests, and also look at trap crops, and also to develop resistance within our crops themselves. So I think that there's lots of room in terms of intensifying or better understanding these relationships and how to optimize these conditions so that we are minimizing pest pressure and thus minimizing the need for inputs. So Dr. Migliorini gave some very nice presentation examples of agroecology and different levels of input use, both in conventional and organic systems. And this slide shows greenhouse gas emissions on the y-axis, and then the contribution of conventional systems, organic with input substitution, and organic with agroecological practices as the 3 bars, according to soil management, pest control, machinery, and irrigation. So we can see that the highest greenhouse gas emissions come under soil management, and where there's high levels of inputs being used. But organic agriculture can cover a wide range of levels of input use. If we are applying high levels of inputs, we also might be resulting in conditions where we lose nutrients, and also where we might have higher CO2 equivalent losses. So for example, from nitrous oxide emissions, which we must be very conscious of. Organic with agroecological practices works towards trying to harmonize the use of the processes within the farming system so that we are not resulting in these losses. Now, this is a continuation of the previous slide, and these researchers were working with blueberry crops, and this was in Chile. And I appreciated it because they were studying organic with inputs versus organic with agroecological practices, and then comparing those 2 systems against conventional. The graph on the left shows the yield of the blueberries, and the graph on the right shows the cost of production. And what you can see fairly quickly is that the agroecological practices can achieve similar yields as conventional management, and they can have lower cost of production. When we start moving towards organic with high levels of input substitution, then we may not be achieving necessarily the same yields. And we might have a much higher cost of production because the cost of organic inputs can be very high if we're trying to simply substitute the conventional inputs with organically acceptable inputs. And we're seeing this more and more, where especially in Canada and the United States, many farmers who transition from conventional systems to organic, they still want to have the same yields, and they want to bring in inputs to support their system. and that can be costly. So the challenges of ecological intensification relate to having a better understanding of how the different components of the ecosystem all work together, and then how we might manage those components so that we can optimize production. But even once we understand that, we still need to be able to apply these interactions in a practical way. So this is where I will start to talk about smart agricultural technologies. And I think that this is an opportunity for us to use our latest technologies to, and we should promote that organic agriculture is using latest technologies to better understand the ecosystem that we work in, and that we can possibly optimize the functioning within the ecosystem by using perhaps some of these smart tools. So what is smart agriculture, and is it fashionable or is it our future? When I think about fashion, sometimes I think about trends, something that will come and go and may not last for a long time. Certainly there's some practices that stay around in agriculture for a very long time until there is a paradigm shift. But there's a lot of interest in smart technology in Canada and the United States, but is it really something that's feasible to be adopted? Will farmers adopt it? And what role could it have in smaller scale production systems is another big question. So let's find out what smart agriculture is. And there's a number of different definitions, and I'm just going to present my kind of amalgamated definition of what smart agriculture might be. Smart agriculture is often also referred to as smart farming, digital agriculture, agriculture 4.0, or e-agriculture. So there's different terms that might be used for smart agriculture. In my mind, the smart agriculture involves the combined use of sensors, data transmission and storage, positioning, and data analysis technologies to detect the condition of an agricultural management unit in an automated way, and to generate output that may be acted on by managers or automated tools. That's a mouthful, that's a lot there. I will go through that in a step-by-step way here in a moment. So, but this may include the Internet of Things. Certainly the Internet has allowed tremendous connectivity between many different tools that we might use and that are available for us to use now. And it may have many applications as well in terms of environmental assessment, crop and livestock management, product tracking, and marketing. And that's what I'll talk a little bit more about here shortly. So let's look at the components of a smart agricultural system as I would describe them. If we begin with the agro-ecosystem, such as crops or livestock or a mixed system, we are pretty much all of the smart agricultural systems will have some kind of a sensor that they are using, and they are detecting something, some part of the agro-ecosystem. And I will be going through lots of examples here in a moment. And so keep in mind that the sensors are always assessing something in the agro-ecosystem. Sometimes those sensors are augmented by global positioning systems so that you know where in the field or where on the planet you might be taking these measurements from. Then we have the transfer of this information that's being collected by the sensors through some mechanism. We used to just use hard wires to transfer information to a data logger, and then we would download that data and analyze it through our spreadsheets and things like that. Now we have much more automated systems for collecting data, and that data might be transmitted through internet or Wi-Fi or Bluetooth systems, or it might go straight up to satellite distribution systems. This data transmission can connect to, especially if you're talking about large volumes of information, it might go to a cloud storage location, where it might also be linked to other data networks. So other data might merge with your data, or you might merge your data with other data. Ultimately, that data will come back together into an analytical system, such as a computer or a phone or a tablet that has software that can analyze the data that is being output. So far, we are gathering information from the environment using sensors. We're transmitting that data and perhaps sorting it and adding to it, and then analyzing it in an analytical system. So this is, I think, one of the key things is in smart agriculture, the latest programming technology, programming and to support technology has been tremendous, and our ability, our computing power has increased so dramatically that now we can gather vast amounts of data, and we have analytical systems that can automatically analyze that data and provide outputs. And sometimes those outputs will make a recommendation or a decision to a producer. So the decision could, if it follows one pathway, it might just send, once again, through data transmission, instructions to an automated action, a robot or an automated irrigation system or something like that, that will act on the environment that we're measuring. Or it might lead to a decision that the farmer will make, and they will use their tools to work in the farm. So these are the components of a smart agricultural system. So what are the goals of smart agriculture? Ultimately, we are trying to increase yield and efficiency, improve animal welfare, make better decisions, improve product quality. We want to enhance control over internal processes, improve soil health, and perhaps even just study or better understand the agroecosystem. It might also reduce labor, input use, environmental impact, and waste or loss from agricultural production systems. And hopefully it will reduce cost by providing us with more precise and optimum application of our resources. So let's take a look at some examples, and we'll start with some precision agriculture technology. Now, I'm going to be giving many examples here, and if I was you, I would be thinking these applications don't apply to India, where the scale of agriculture is very small and farmers cannot use these technologies. And I want you to think about not so much whether the specific technology is applicable to your operation or your operations in India, but rather think about the possibilities of how you might incorporate these technologies. Open your mind to possibilities and imagine what might be done. And there might be a way to use them, but we need to decide if that's efficient or effective. So we know that the landscape is extremely variable, that the soil can vary tremendously within a short distance within a landscape. And so many of our, the latest applications of precision agriculture and smart technologies are relating to more precise management of inputs on the landscape. So data that's being collected about the soil or crops are being used to allow us to more precisely apply inputs where they're needed. So that should save money in terms of not wasting inputs where they're not needed, and also provide more effective or control of pests or enhancement of productivity where it is needed. So some of the interesting technology that's being developed now includes, in terms of soil mapping, include automated sensing systems that are being built right into a unit that can be pulled behind a tractor. And so This unit here, for example, has a GPS system, and then it has a shank that goes into the soil, and the soil the shank has a number of sensors on it that can detect soil properties as you're pulling it through the field. So you can generate very precise maps. This is data that's generated from a different system that was produced by Toyota, a very similar kind of concept. And but they're collecting over 30 variables at once as they are pulling the tillage equipment through the soil. So this is very modern technology. And obviously in these fields, you can see very precise measurement of different soil properties. And you can generate maps of soils in these areas. Now, of course, this takes a lot of time, and you can imagine that there's a lot of data that is being collected. And certainly you need to have the capacity to handle all of that data. But the result can be that you can generate a map that identifies problem areas in the soil where you might apply amendments or perhaps enhance fertility. In other areas, perhaps the soil is really good and you would not want to apply excess amendments there. Another sensing technology, again, we're talking a little bit about sensors here, is remote sensing technologies. So when I first started studying in agriculture, remote sensing was primarily limited to aerial applications, so planes, and also to satellites. And the precision of that sensing was not the best. However, now we have drones that are available to us that can be include a number of different sensors, and we can have very precise measurements of different characteristics of the landscape, even within a few centimeters in terms of positioning, very high resolution. So you can see that there's a number of different sensors in the bottom right of the screen. You could have simple visual photography, you could collect video, but you also might be looking at reflectance of different wavelengths of light that are being gathered. You also might look at LiDAR, which is light deflection and absorption. And then you have thermal, so heat sensing, and then hyperspectral and combinations of different wavelengths that you might measure at once. And there's even guides for how agriculture can be used in agriculture or in drones that are developed by the Food and Agriculture Organization of the UN. So what kind of data would we collect if you're not as familiar with this data? You could collect basically balances of different light that is being reflected from plants. And the balance of red, green, blue, and near infrared can be a good indicator of the health status of the plant. Or if you're looking strictly at the near infrared and the shortwave infrared, you can measure the moisture index of crops and identify areas that are deficient in moisture or that have excess moisture. So depending upon the kind of data that you're collecting, you can measure the height of plants, you can measure the potential, the density, the biomass production of plants. You could identify different types of plants within a field, so weeds could be distinguished from crop plants, and you can assess the health of the plants. So here's an example of this kind of technology that's creating maps of a vineyard in Nova Scotia, Canada. And so you can see that there's different variables that have been measured depending upon the different sensors that are being used. And so you can look at the whether there's problems within your vineyard, such as plants that are not performing very well, or if there's low levels of vegetative production. And then you can target those areas with your nutrient management plans or perhaps pest management plans. You might also identify areas where there's gaps in the field that you might replace plants. And you look at water content in the soil to determine irrigation. And you could also very carefully map your landscape to identify the shape of the land and optimize your management system. So this is especially beneficial if you are a larger operation and you do not have the ability to very carefully walk through all of your vineyard. But I've also seen these kinds of technologies being used in large greenhouses. And because you cannot see some of the wavelengths that are being emitted, such as infrared wavelengths, are not visible to the eye. And so by flying a drone in the field or in the greenhouse, you might be able to detect stressors before you see them with the naked eye. And so how does this apply to small scale agriculture, smaller like fields, and where you have many individual farmers that may only have 2 hectares of land? Will they buy a drone and fly it around and get the training and handle all the data? I don't think so. And even in Canada, in large scale operations, many of we have contracted service providers that will go to farms and provide services to fly the fields, analyze the data, and give it to the farmer. So perhaps this is an opportunity in organic systems and in India or other small scale production areas to use shared resources to gather information about a region. And so we need to be creative about how we apply these technologies in a useful way. Here's a large combine harvester that's quite common in Canada, but will you see this in India? Probably not too often. You might see it in some rice, not perhaps this size, but that's not the point. I'm giving you another example of how these sensors are being used. So this harvester will go through the field, and as it's harvesting the grain, it will be gathering information about the grain in terms of the moisture of the grain, the yield of the grain by measuring, there's different types of sensors that can measure the yield of the grain as it's coming into the harvester. You have a global positioning system, and all of those things combined will go into an analytical system that will provide output to the farmer and generate maps such as what you see here, indicating where there are good yields of crops and where there are poor yields. You could supplement this with strategic soil mapping programs. Even if you don't use like the smart tractor technologies, which are still not really available, you could use these kinds of maps to identify the areas that are problems and focus on those areas. So there's lots of different sensors that are also available to measure what is happening to crops and in the crop growing environment. Whether it is measuring the humidity level on a leaf surface to measure disease, the potential for disease, so leaf wetness, or if you're measuring environmental conditions or the moisture or nutrient status in the soil. There are many different kinds of sensors that are now available. And many of these sensors are now being connected to satellite phone systems or cellular phone systems that can transmit data even over long distances to operations. And you can identify if there's a problem in your field, and if you want to, and perhaps have some sort of a response automatically applied, such as irrigation or pest management. Here's an example of irrigation systems. So this particular company has different sensors that are solar powered and measuring incoming radiation as well, and measuring soil moisture content content at different soil depths. And it is providing an automated system of analyzing moisture content and perhaps even triggering your irrigation system to operate when you've reached a certain threshold. So we can have much more efficient use of water so that the irrigation will turn on and off when needed. Okay, let's talk a little bit about precision weed management. This is really interesting, and I gave some presentations in Vietnam about a year and a half ago, and it was interesting because there was a wide range of representation from many different countries. And some countries, researchers were saying, well, we do not want to have robotic weed control because that will displace labor. We need to find jobs for many people. And in other countries, there's a shortage of labor, and so we need these technologies to help better control weeds. Certainly in Canada, we actually bring in a lot of labor from foreign countries to help with our production systems to provide labor. So many farmers are looking at more automated systems, especially once they become larger operations. So you can see the different types of robots here that are being used for weed control in different types of cropping systems. One type of robot that's, or well, not a robot per se, which is fully autonomic, is attaching camera guidance systems to your tillage equipment. And this is actually something that is being adopted quite a bit by larger scale farmers in Canada, where the camera is sensing the position of crops or rows of plants, and it is adjusting the tools on the tractor so that it is moving around the plants or going between the plant rows to control the weeds. And so very interesting technology, and it's one that is being adapted or adopted fairly quickly by larger farmers, especially for precision weed management between narrow rows, where they now have cultivators that can go between the rows that are hooked on tractors. So very interesting. But there's also spraying technologies that are being developed. And I find these are interesting, not just from the perspective of weed control, because there's very few herbicides that are available on organic farms or for organic agriculture to use. But this kind of technology could also be used for the application of micronutrients or compost teas and making much more efficient use of inputs that we're applying. So you can see here that essentially what is happening is that a sensor is detecting and differentiating between plants and weeds and will target the spray application where it needs to be, and it will avoid the plant that's not supposed to get it. So in this case, it's a weed, so the grass is being hit by the spray, but the crop is being missed. So very precise herbicide application, and perhaps there's a lot of debate. I'm not sure that we want to go to developing organic herbicides, but if we want to use compost teas or biostimulants or micronutrient applications, we could perhaps have much more impact by using this kind of technology. So is it cost effective on small scale operations? Perhaps not. However, if you are sharing a resource within a region among many farmers, perhaps it could be more useful. This is an interesting robotic weeder that not only has the detection system to identify where the weeds are, but it also can identify what kind of weed there is and decide whether it should use a herbicide or a tillage tool. You can see the little tool, the hoe coming out of the machine, and it's actually removing a weed. And it's solar powered, and so when it runs out of energy, it goes back to a docking station. So these are just ideas about the applications of smart technology. We need to think about organic agriculture and how we might use these kinds of concepts in an organic appropriate way and suited to your scale of agriculture. So keep that in mind always when I go through these. Early detection of diseases and insects. So again, there's many different sensing systems that are detecting the environment and where you might have disease pressure and or insect pressure. There are modeling systems that are being developed that will predict when a pest will arrive, so insect or disease pressure. And so this is the kind of research that we could be doing for different insects or diseases, and knowing their life cycle, knowing how many heat units are required for those pests to become a problem. And using, again, this could be, have a single weather station within a local region, and that could help local farmers, many local farmers, identify when the appropriate time is to be watching for pest problems. This I find is an interesting application where that I think is very suited to organic systems. It has a pest monitoring system that will identify whether, and also an environmental monitoring system. So those two things will monitor when pests are present, and when the pest becomes present, it might release a pheromone that's a mating disruption pheromone for insect control in apples, for example. So, so you can release pheromones and basically confuse the male of the pest, and it'll disrupt the mating, and then you'll have less disease pressure. So, but this is a very integrated system that is monitoring environment, monitoring the pests, and then in an automated way, even releasing the pheromone disruption. So very, very interesting technology. Here in Canada, we have research that was going on delivering the trichogramma wasp, which is a parasite of the European corn borer. And we know that the trichogramma wasp will parasitize the corn borer, but it's hard to distribute these pellets of trichogramma wasp that include the larvae evenly throughout larger fields. And so this company in Quebec, Canada, developed a drone system that would deliver the pellets of trichogramma wasps throughout, evenly distributed throughout a field, so that we could enhance the predator population of the pest. And so very interesting application. And more, we're even starting to see aerial application of through drones of different sprays. And again, it doesn't have to be a pesticide. It could be something that's a stimulant that is more targeted application. So just let's use our imagination about how we might apply it in organic. I do want to talk about livestock management very briefly. I'll go through this quickly, but I think it's interesting that there's lots of technologies that are also being applied to livestock. And part of organic agriculture is to enhance productivity, our goal, but we also want to support animal welfare. So one of the challenges is monitoring the livestock to ensure that their welfare, their health and welfare is being supported throughout their life. And there's more and more systems or sensors that are being developed to detect what is going on with livestock. So for example, this is a simple example that I've shown here where you can have a bioacoustic sensor, so it's something that's a listening sensor that will detect if there is a problem within a poultry barn. And so if there's all of a sudden a lot of noise in the barn, or if the, you could also train the sensor to detect coughing in the barn, and you could identify whether animals are under stress or if they might be sick. And so you might be able to identify things that are going on before you might see them if you're walking through the barn, because we might not be there all the time. Again, this might be an application for larger scale livestock production, but still I think it's interesting. And if we're thinking about organic and livestock, we should be automatically thinking about welfare and how can we improve it. Here's an example from Alibaba Group Holding in China that has developed a very sophisticated system in their pork operation. They're labeling all of this isn't an organic system, by the way, but I think that it potentially could have applications in organic agriculture. So they label their animals with a tattoo, and they use visual identification systems. So cameras can detect the movement of all of the animals anywhere in the barn or outdoors, wherever the cameras are. And they have acoustic sensors in the barn that detect unusual noises. So if a mother pig is laying on the piglets, they will squeal and they will come running. They also have thermal sensors, so they can detect if the pigs are, their body temperature is increasing. So you could detect issues such as illnesses or perhaps pregnancy, cycling issues very quickly and easily in the barn. So very interesting potential applications, and they can also, just by measuring the body size of the pig, measure how fast they're growing. And then we have, they can also put sensors on to track their movement of the pigs and measure how fast and if they're getting adequate exercise. And this company is actually saying that we want a pig that can run 200 kilometers instead of weighing 200 kilograms. So they felt that the quality of the final product of the pig was related to the amount of exercise that it received and not necessarily their size. In other livestock systems, this is in Europe, we've seen the development of robotic milking machines, but this is even going further where the robot is in the field and it is following cattle around in the pasture system. And so it saves the cows from to walk all the way back to a barn. This might not be an issue in India because your fields are much smaller, but in other parts of the world, the energy expended by livestock moving back to the barn and then coming out again to graze is significant and can reduce productivity. I see I'm running over time, so I'll be quick. I want to talk very briefly about handheld tools. And so the technologies aren't all big. Many of these technologies have become really small as well. And so you can see many technologies and software that's being adapted to cell phones. And this is something that is accessible to producers almost everywhere around the world. And in many parts of the world, growers do not have good access to really good agronomic advice. And sometimes they have language issues. And these and phones, the technology on cell phones now is so sophisticated that it can really help farmers. This is an example of just measuring the greenness of a leaf to see what the nitrogen content is in the leaf through a standardized chart. There's other systems such as this one that are multifunctional. You can take a picture of a plant and identify what it is. You can detect the amount of damage on a leaf surface. And even there's that yellow dish is a sticky dish collecting insect pests. And you can analyze the population of pests within that dish. There's a system called Plantix, which I kind of like, and there are some examples from India that does very similar things, as I just mentioned. It also measures nutrient deficiency symptoms. So you can take a photo and it'll help to determine what the problem is. But this is complemented by a blogging system or a networking system that allows farmers to communicate on the internet and ask for solutions. So first of all, this was actually a question that came from India, and they said, is this ash weevil and how do we control it organically? And then they got a response from Pakistan and another response from Europe that helped to provide solutions in an organic way. So this Plantix system is actually designed for smaller scale production systems in developing countries and creates this community of resources. So I think it's something to look into. Then we get into some more really sophisticated technology, and this one really surprised me. And here we have a regular cell phone, and it has a software on it that's loaded on, and this is new technology as well. But it is attached to a small sensor that is doing basically assessing the volatile organic compounds that are being released by a plant. So in this case, it's detecting late blight, which is common in tomatoes or potatoes. And you can see they just took a piece of leaf, they put it into the jar, they close the jar for about 15 minutes and allow the volatile organic compounds to release from the leaf. And then that straw is sucking the compounds into the detection system that then will indicate whether or not there is a late blight problem with in the plants. So it's, I think we are limited by our imagination in terms of how we might use these technologies. And certainly this could give us advanced notice, even if you have one unit like this that's developed that can detect problems in an area of India, you could then use it in many local areas to help be proactive in managing pest problems. So this is perhaps some of the future of where we might go. But we also see sensors being used in cell phones in marketing and tracking of products throughout the whole organic value chain. And this is also really important. I am not going to talk any more about it, but it allows consumers to make a direct connection to the farmer and to the whole production system and where it might be raised. So very important and potential for using these sensing technologies on phones to augment marketing and tracking systems. So I'm going to wind down here now. How can smart technologies be applied to organic agriculture? And I think that it is limited by our imagination. Many of the technologies that are developed now are not necessarily applicable to organic or to our scale. Sometimes they're not even being adopted by large conventional farmers because they don't see the advantage of the cost effectiveness of the system, or they're not prepared to invest in it. So we need to be very careful about how we use these technologies, but design them with organic systems in mind. I think that we can use these systems to better understand what is going on in our organic agro-ecosystem. And so nutrient cycling, biological activity, disease and pest pressure, I think if we can understand, and the rate of plant growth, if we can understand our agro-ecosystem better, then that will allow us to better adapt our performance, our management practices. So ultimately, I think that smart agriculture does have some potential for our organic production systems, but we need to design it appropriately. So in conclusion, the capabilities and applications of smart agriculture are growing rapidly. There's many benefits. Sometimes, however, it's very complex. It can be very data intense. You can collect a lot of data in a very short period of time with some of these sensors. And that data needs to be stored somewhere. And if it's in servers, these servers take a lot of energy. There's actually environmental concerns around data storage. So we need to use these technologies carefully because we could very quickly overload ourselves and our systems with data. There's also data storage and security issues. So you need to have, if it's, you may have security concerns around the data that you collect. So in organic farming systems, I think that we need to be focusing on using these tools in an ecological way to augment our ecological practices and intensify our systems in an ecological way. It might mean that we are developing resources that can be shared among many producers, and not necessarily because we might not be able to justify the cost for individual producers to have them. So smart technology needs to be smart for organic, specific, measurable, achievable, relevant, and time and cost sensitive. So I think that we move forward by developing local case studies to demonstrate and test how these technologies might be used. And then we can move towards wider adoption. So that's my presentation. And I guess I'm a little bit over time, so I'm not sure how much time we have for questions, but I'll stop now.
Thank you, Dr. Andrew, for your informative presentation, and that you have enlightened us with various multivarious topics that is included ecological intensification, automated plant intensification, and precision spraying, green gas emissions, smart agriculture. Similarly, you have included in your presentation that is biostimulants, precise and time-sensitive placement of the biocontrol, aerial planting and spraying technique, and one of the thing is that smartphone-based fingerprinting of volatile organic compound. So that is very interesting subject in the today's scenario of agriculture. Sir, I am sure that the precise knowledge that you have presented here will definitely help us to students or academicians, scientists, those who involved in this particular area of future studies. Once again, thank you, sir, for your informative presentation. So now the topic of this presentation is open for discussion, sir.
Andrew, one question from Dr. Sandeep Menon. I'm just requesting Sandeep just to ask. I'm just unmuting him. Yeah, Dr. Sandeep Menon, please.
Sir, thank you, Dr. Andy, for your nice presentation. It was really worth presentation. I have one doubt. You were talking about the use of robotics and the camera-based weed control management equipments. So I'm doubtful about the mimicry weeds. What about the mimicry weeds? Are your robotics or your camera-based those machines, they are able to control the mimicry weeds?
Sorry, which kind of weed? Sorry?
Mimicry weeds, which are exactly morphologically identical to the main crops.
Oh, yeah, so that would be much more difficult. And we actually have researchers on our campus that are training systems to identify weeds. It requires very intensive software configuration and training to identify that. But if it's exactly mimicking the crop, then obviously that would be very difficult in terms of spot application. There's no question. However, sometimes some of the systems that are camera guided that follow rows of crops, they will be, the weeds are not always present throughout the whole row, so or throughout the whole field. And so the camera can still detect the rows and keep tillage equipment between rows. So it depends on which approach you're using, but it's I think there are limits for sure. And you definitely want to make, I'm amazed at the technology and what it is capable of doing, but it definitely requires a lot of programming to make sure it's safe.
Yeah, now I'm requesting Dr. Dharamraj Singh. Dr. Dharamraj Singh.
Mute me. Okay, thank you very much. Dr. Andrew. I am a Dr. Dharmaraj C. Jetwa from Junagadh Agriculture University from Gujarat, India. I am working on matting disturbance of the pink bollworm as well as brinjal shoot and fruit borer from last 5 years. I have one doubt regarding that. How artificial intelligence we are using for this mating disturbance? And one another question is that, for you are talking about the Trichogama Chilonis or any species, so how we use this artificial intelligence in Trichogama also?
Right. Okay. Well, I'll start with the trichoderma, and I think that this is where I think we need to use our imagination. We need to better understand the soil and biological diversity in the soil and factors that influence a healthy soil environment for crops. And the trichoderma application, like I loved the presentation that was given earlier this morning because it was very practical. And but I think for me, it's using smart technologies could be used to sense the environmental conditions, better understand where the trichoderma is present, and also other organisms as well. And perhaps we can develop technologies that will better assess biological diversity in the soil. So I was using that as an example of ecological intensification, where we need to optimize those systems. And that in my case, I was thinking smart technologies could be used to better understand whether it's any kind of biological control in the system that it's growing in. So and your other question, I think it was a little bit hard to understand, but it was relating to assessing damage from a fire. Sorry, I can't, you're muted.
Trichogramma. You was asking regarding trichogramma.
No, I am not regarding Trichogama. Mating disturbance, you know, the mating disturbance we are using, sex pheromone mating disturbance we are using for the management of either pink bollworm or maybe any pest. So how artificial intelligence we are apply for this mating disturbance? So many in America, and you can see that in Canada also, maybe there is a available of pest or something like that, droplet like that, for the management of the pink bollworm, mating disturbance, sex pheromone traps are available. So for in one of the side you discussed that the mating disturbance used for the artificial intelligence or maybe in a smart agriculture. So my question is how this mating disturbance we are using in a smart agriculture.
Yeah, so in this case, the mating disruption was linked to automated sensors that were detecting when the pest became present so that it could automate or optimize the timing of release of the pheromones to disrupt the mating. And so, so it was monitoring the environmental conditions as well. So you could, you know, often the heat units, or in Canada at least, many of our pest cycles are connected to heat units or growth cycles. And so if you're monitoring environment, you can predict when problems are arising. But it also had a system of sensing the pest itself when it was present and detecting the pest. And it's been with traps or an automated system of detecting the pest in a trap. I think that's the way it was, but then it automatically released the pheromone. So the farmer did not have to be there to start releasing the pheromone. It could do it right away when the pest first arrived.
Now actually many people have raised hands to ask questions because it was a very nice and very informative lecture. So I'm just allowing Mr. Pankaj Prasad Joshi. Pankaj Prasad Joshi. Can you hear me? Pankaj Prasad? I think he's not there, so we'll just move to Sudhakar Metil, please. Sudhakar Metil?
Hello.
Yeah, please.
Am I audible?
Yeah, please.
Sir, I would like to ask you a question. Actually, you are from Canada, and Canada is a developed nation. While thinking about India, India is presently a developing nation. So such a type of using technology, such type of technology, making use of stick technology in India, can it be affordable to Indian farmers? And what could be the cost of the end product?
Yeah, I think that that's a very appropriate question, and it depends on the technology, but I don't think that, you know, because the scale of agriculture is for individual farms is so much smaller.
Andrew, you are muted. Andrew.
Okay, somebody must have muted me. Okay, so it was a good question about the technology and whether it can be used in smaller scale production systems. And I've had that question in other places. When I was in a training session in Vietnam, where we had lots of different Southeast Asian countries represented, that was probably one of the biggest questions, was how do we apply this technology in our smaller scale production system? And this is where I think it is not about individual farmers using the technology, but perhaps training individuals, agronomists within a region to be able to use the technology and interpret the data and to support farmers. So if I was setting up a pilot project in India, I would be going to a region where there's lots of organic farmers and having a trained expert that would be working within that region and supporting many farmers with the technology and not just one farmer. So, so it become a shared resource. And of course, with farming, you know, we always want to see a return on investment. And even in Canada, where I have talked with farms as large as my brother, he has a farm that's about almost 1,500 hectares in size. And he even is not sure that, that the data that he gathers would be useful. But sometimes he's using the technology already and he doesn't know it. So, so I think that there's, I think this is where we need to adapt the technology and be creative and keep it in mind and use it where it makes sense. I'm not trying to advocate and tell everyone to use it. I'm seeing that this technology exists and it may be something that we could use in the future.
Okay, thank you, Andrew. Now I'm just taking one question from chat box. Actually, you have presented both the slides on organic agriculture and smart agriculture. So the question of Dr. M. Mudasir from it's organic culture is better option than smart agriculture. Which particular system is more better, either organic or smart?
Well, I think that organic agriculture, well, I guess the question of my presentation was, should organic agriculture be also smart agriculture? And in terms of technology, they are not exclusive to each other. I think that and this is what I am exploring when I look at smart agriculture technologies, is how can we use them to help organic agriculture? I don't think it's one or the other. And I think that smart technologies could be applied in organic situations, but it needs to be used appropriately. Yeah, to make it worthwhile. So this is, you know, again, this is an exploration. You know, for me, it's an exploration and thinking about outside of my normal box, outside of where I normally think, and how can I, if I'm trying, when I meet with government officials here, they are looking at very modern science and modern technologies, and they want, if we present organic agriculture as only being traditional practices, then it will feel to our government like they are going backwards, that they're not supporting forward movement in agriculture and science. And so part of what I want to do is look at how we can use technology to support organic systems, but is still within the principles of organic and effective in organic systems. I hope that answers your question.
Yeah, still actually many more hands are there just to ask questions. So can we have one more or two more, or shall we just break?
I can answer, yeah, probably. I need to leave in about 5 minutes.
Okay, so we'll have a last question from our coordinator, Dr. S.D. Zadav, please.
Dr. Andrew, in one of your slides, you have mentioned that biostimulants, various biostimulants, which includes humic acids, some protein hydrolysates, seaweed extracts. So most of the biostimulants are extracted chemically. So can you consider that biostimulants are organic, or whether it is a component of the precision agriculture? Because most of the biostimulants are extracted chemically.
Yes, and so interestingly, I was just reviewing an article relating to the use of saponins for insect control in vegetable systems, and using saponins extracted, say, from tomato leaves. And so the question did come forward, how is that saponin being extracted, and is it still organic if it's being extracted that way? And I think it varies, depends a little bit on the organic standards within different countries. There are some permitted extraction techniques. So certainly whenever we are looking at different kinds of inputs for organic systems, they always need to meet the organic standards. And so, so there are some biostimulants, I think, that are on the market that here in Canada that are approved under organic standards here in Canada. But I am not an expert in this area, so I don't know the extraction process that was used. But yeah, so I think I'll leave it there. I'm not sure I can expand further.
Thank you, Dr. Andrew. Very nice presentation, informative presentation. So I request Dr. Kunde, Dr. Gaur to propose a formal vote of thanks.
Thank you, Dr. Zadav. So friends, we are at the end of this technical session on the third day of 6-day webinar on organic farming field to fashion. I am very much happy to deliver a vote of thanks on behalf of CORE, Center for Organic Agriculture Research and Training, Dr. PDKB Akola. First of all, I am very much thankful to our Honorable Vice Chancellor, Sir, Dr. V.M. Bhale, for his constant support and encouragement for successful conduction of this event. I further extend my thanks to today's speaker, Dr. Andrew Hemister, Director, Organic Agriculture Center, for his informative and high-tech lecture on agriculture, organic farming management. Lastly, I am very much thankful to the participants without whom this session could not be successful. And thank you once and all. Bye-bye.
So friends, thank you very much. And again, I am just take this, I would like to take this privilege, and I would like to place my very sincere thanks to Andrew for sparing his very valuable time, and I extremely sorry for disturbing you time to time for your own convenience. And definitely I am confident all participants from all the countries as well as the participants from India itself must be delighted and must be upgraded their own whatever the ideas regarding high-tech agriculture, and the you have already touched all the components of organic agriculture, and even you have placed the directions for further research. So thank you very much, Andrew, and I hope the consistent cooperation in future ahead, because this university will definitely take an advantage of your expertise, and we assured and definitely will just come across again for further webinar, as well as you are always welcome to Dr. PDKV Akola for further collaboration and research. Thank you very much.
I look forward to such an opportunity, and thank you again for all of the support and the opportunity to speak. It's very nice to connect in India, and it's very useful for me to understand or hear perspectives from India, which is a very different country and very different agriculture than we have here. And once again, I very much also, Dr. Miglarini talked about how important India is in terms of organic producers and the history of organic, and I fully agree. So I look forward to future interactions.
Thank you. Thank you very much.
Thank you.
So now this was today's session. Today we have just come across with morning in Dr. Paula and the evening with Dr. Andrew. So for again tomorrow we have a very good discussion with another speakers. So tomorrow morning we'll have a panel discussion on value chain and market linkages for organically produced crops at global platform. So it's a panel discussion, and many panelists from various countries will be joining this session. So it's an extremely important session, because we always used to say the market and value chain for organically produced products. So I request all the participants to join the training session by 11:45 in the morning. Just note this particular time, because today we had started at 1:30, but again tomorrow we will be starting this session at 11:45. And again in the evening, Dr. Van S. Harold from Cornell University, US, he will be sharing his ideas on soil resilience and magnitude of organic farming. So Cornell University is the top 5 universities in the world. So I request all the participants just to join without fail. The links for the same will be sent to your groups. So thank you very much for joining. We'll meet soon tomorrow morning. Thank you very much.